Okay, so this unit, electrochemistry, is all about the electron. And in order to understand what's going on with electrons in a reaction, we need to take a look at the terms oxidation and reduction. So if you look at the picture I've got here, now mine's in color, yours is not, what has happened is that a solid piece of copper has been put into an aqueous solution of silver nitrate, and as time has gone on, the solution has turned blue, and you see sort of this fuzziness. Occurring on the copper metal. Now, first of all, let's talk about the blue. The blue is due to copper plus 2 AQ. So copper plus 2 AQ is equal to blue. So what's going on here is, you would have seen this in grade 10, this is just a simple single displacement reaction. And what you see is copper is becoming an aqueous solution over here, and silver is becoming a solid. We'll see later why that happens, but for now that's just what's going on in the picture. So the first step in doing this is to write out an ionic equation. So all I've done really is I've just split up all the AQs into their two parts. And there they are. So AgNO3 becomes Ag plus, and we've got two of them here because we've got a 2 there. So that's the balance. And then what we've got is, we've got all these ions here, but you'll notice you've got 2 NO3 on either side. We call those spectator ions. So NO3 1 minus is equal to what we call a spectator ion. And they're just not involved in the oxidation reduction process. And so what we're left with is this, which is just the things that are involved in the oxidation and reduction. Now let's look at that. I told you it's all about the electrons being moved. So if you look here, we'll look at silver first. Silver has gone from +1 to no charge. So it has got more negative. It's gone from +2 to a 0. So what has happened is the Ag plus 2 electrons have been gained here. 1 electron per Ag. Now those electrons had to come from somewhere, and if you look here, copper goes from 0 to +2. So one copper ion, or one copper solid, lost 2 electrons. So 2 electrons lost per Cu. And that is what an oxidation reduction is. Something gains electrons and something loses electrons. So if you look in your notes there, you see that oxidation is the loss of electrons and reduction is the gain in electrons. That's something you need to know, and we'll see it a lot, so that'll be something that you just become really familiar with. So here I've got another reaction, and once again what you see is it's a single displacement reaction, okay, similar to above. And I've brought it down to, I've simplified it so we're not involved in the SO4, because again, they're not involved in the oxidation reduction. And we can talk about that in class, what that exactly means. So we see zinc has gone from +0, no charge, so we can put a 0 there if you want, to +2. That means that it has lost electrons. It has donated its electrons to something else. So we say it donated electrons and it has undergone an oxidation. Well, where did those electrons go? The electrons went from zinc over to copper +2. All right, and that would have been 2 electrons. So copper has accepted electrons, and we say it undergoes a reduction. Now the tricky part of these things called oxidizing agents and reducing agents. So the easiest way, I guess, to look at it is copper gets reduced. Copper 2 plus gets reduced. Well, something had to help it get reduced. It needed electrons. So that's why we call zinc the reducing agent. It helped copper become reduced. Now, zinc lost 2 electrons, and what made it lose 2 electrons? Well, copper made it lose 2 electrons. So zinc lost 2 electrons to copper. Copper 2 plus was what we call the oxidizing agent. It made zinc lose the electrons, and you can see the definitions down there. Now, as we go through the unit, this right here is extremely important. I would put a star beside that in your notes. You cannot gain or lose different numbers of electrons. So if an atom loses 4 electrons, they have to go somewhere. You don't have this cloud of electrons that aren't used in the reaction. So those numbers, lost and gained, must always add up. And you'll see when we start getting deeper into the unit how we're going to see that. One of the things that we're going to see in the unit is these things called half reactions. Now, a half reaction, you break up the oxidation to reduction into 2 parts, as you see there. Now, in half reactions, you actually, what I say, you see the electrons, and E minus is short form for electrons. You actually see them. Up here, you don't see the electrons anywhere in the equation. So what we've done is we've split it up into 2 parts. The one that got oxidized and the one that got reduced. So zinc is losing 2 electrons to copper plus 2. Okay, the reduction occurs on the Cu2 plus. Now this will always take place. An oxidation will always have electrons as a product. So always a product right here. And in a reduction, the electrons are always a reactant. Okay, and we'll start off, you can see the whole thing right there. The example that you see under there, you can give it a try yourself. In fact, I encourage you to do it. We're going to use this one as a model, but we'll start with that one in class just to get a feeling for this whole oxidation reduction thing. Now, an important part of this unit is something called oxidation numbers. And if you read the definition there, it tells you what it is, but I thought I'd give you some examples. Long story short is basically you have covalent compounds. We are going to treat them as if they are ionic compounds. So as if they were a metal and a nonmetal, where metals transfer their electrons over to nonmetals. That's nothing new from you, and that's what we call an ionic compound. So for example, if we look at water here, and if I draw sort of Lewis dot diagram of water, it's going to look like this. Now, if we put on our dipoles, they would go towards oxygen. Oxygen has a higher electronegativity than hydrogen. And what you learned last year, and we talked about it this year, is because this is a covalent bond, you're only going to put a partial positive on each hydrogen and a partial negative on oxygen. And so this is a covalent compound, and that's what we'll do. What we're going to do is we're going to assume everything, including covalent compounds, act like they are ionic compounds. So over here, I'll just do an example. If you had Na2O, that is an ionic compound. We have a metal and we have a nonmetal. So if we sort of broke that up into its ions, Na is +1 and oxygen would be -2. And you can look up on the periodic table. Sodium is in the first column and oxygen's in the sixth column. So you can see the ions that they are going to form. So what we're going to do is when we look at or water here, we're going to treat it as if it is a ionic compound. So really, these electrons here between the hydrogens and water are being shared. But what we're going to do is say, well, let's assume that oxygen gets them. And it's a really good way of keeping track of electrons in electrochemistry. So what that would mean is each hydrogen, because it lost an electron, is +1. And the water, because it gained 2 electrons, it will become -2. And that's what basically oxidation reduction numbers are. Now we're just going to apply them now. You have in your notes that the sort of rules there. I'll let you go over them. I'm thinking of making a separate video for this. But for now, I've given it to you in the notes. Basically, everything you need to know about the oxidation reduction numbers, how to put them, some exceptions, and in class I'll sort of tell you the route that you go for sort of the more complicated ones. So let's just do a couple of examples and see how this works. All right, so it says, what is the oxidation number of carbon in methane? I'll mention this later in another video. However, what you want to do first, sort of the map you want to do, is first start with group 1 or group 2 atoms. So you're going to start with group 1 or group 2 atoms. Do we have any of those? All right, not including hydrogen. All right, so group 1 or group 2 atoms, not including hydrogen. Then what you're going to do is you're going to look at the hydrogen atom and see if hydrogen is present. Third, what you're going to do is then you look at oxygen. And then you do your other ones. So that you're going to see is going to help you, especially when we get into more than 2 atoms in a compound. So if I'm going to follow this sort of little route here, it says here I'm going to start with group 1 or 2 atoms. I don't have any. Carbon's in group 4. Hydrogen is in group 1, but we're ignoring it. All right, so maybe I'll write that here, except the H atom. All right, so we don't have that, but we have a hydrogen atom. So I'm just going to put it right here. And hydrogen is +1. Now, if you've got 4 pluses, because 4 times +4 is +4, you'll notice this whole thing doesn't have a charge. It doesn't say CH4 +1 or CH4 -1. It's CH4 0. So what I need to do is I need to add something to +4 to give me to 0. Well, that's the only thing there is -4. So -4 plus +4 will give us 0. So whatever I have for my other atom has to multiply to -4. Well, I only have 1 carbon, so carbon has to be -4. So how did I get this number here? I went 4 times +1 equals +4. And now I check 1 carbon is, we have 1 carbon times -4 for the carbon equals -4. Sorry, -4. And so they add up to 0. Okay, and that's basically it. So carbon is -4 and hydrogen is +4. What is the oxidation number of manganese in MnO4? So let's just start here. I've got MnO4 1-. So in this one, you see, whatever I write in for manganese and oxygen, it has to add up to -1 now, not 0 like above. So I go through my map here, I guess you want to call it. Are there any group 1 or group 2 atoms? No. Are there any hydrogen atoms? No. So now we go to oxygen, and oxygen is going to be -2. So if oxygen is minus 2, what's my total add up to? 4 times minus 2 is minus 8. I only have 1 Mn, so what charge do I have to put here? So whatever number I get up here, it's going to add up to minus 1. Well, if I put here plus 7, 1 times plus 7 is plus 7. Plus 7 plus 8. Plus 7 plus minus 8 equals minus 1. So these oxidation numbers here multiply by the number down here to give you your overall positive and negative charge. And that is basically how you do oxidation numbers. Now, one thing we're going to be checking is oxidation and reduction. And sometimes people get confused about what you're allowed to have as an oxidation. So let's take a look at this. As it says there, an oxidation is an increase in oxidation number. However, that does not mean oxidations are always positive. So one example of an oxidation is, what if on your reactant side an atom is plus 2, and on the product side it has gone to, say, plus 5? That is an increase in oxidation number. Plus 2 to plus 5, it's becoming more positive. However, sometimes people have trouble with this being an oxidation. On the reactant side, an atom is minus 4, and on the product side, now the oxidation number is minus 2. Well, that is also an example of an oxidation because the number is getting bigger. Minus 2 is more positive than minus 4. So I guess a quick way you could say this is number is getting larger. Okay? In other words, more positive. So more positive, towards the positive side. Let's take a look at a reduction. So in a reduction, using the same numbers, on the reactant side, an atom is plus 5. And on the product side, it becomes plus 2. And again, you'll see the number has decreased. Well, if I have an atom that's negative 2, and on the product side, it becomes minus 4, you will see in both those cases that the number is getting smaller. It's becoming more negative. So more negative. So what doesn't matter here is whether it's a plus or minus, but when you go from reactant to product side, is the number getting bigger or smaller? Now, one thing when you're doing this, it's this. You'll see later when we're putting positives and negatives on all our atoms, on the reactants and products, a number has to go increase in charge. In other words, there always has to be an oxidation and a reduction. You can't have an oxidation without a reduction. You can't have an oxidation without a reduction without an oxidation. Okay, you'll see as we go through some examples what I mean by that. You have to have both. A number has to go up and another one has to go down. So let's finish this up with one example here. Now, you'd be given this equation. I wouldn't expect you to go from a word equation into this in this course. So what we're going to do is we will put on our oxidation numbers. Now, zinc here, there's no number. There's no plus, there's no minus, so it's going to be 0. Now, hydrogen is going to be plus 1. And looking on the periodic table, chlorine is minus 1. Hydrogen, no charge, and it's 0. And zinc, now in this one, you want to start at zinc, but we don't know what zinc is because it's in the middle of the periodic table. It's a transition metal. So we can look at our periodic table and see that chlorine is minus 1. And I've got 2 chlorines, so 2 times minus 1 is minus 2. I only have 1 zinc. It has to be plus 2. Okay, So what we're going to do now is, like we did when we started this unit, is we're just going, or this section, is we're going to turn this into its ions. So we would have zinc solid. This would become 2H plus AQ plus 2Cl minus AQ. I'm just breaking it up and making sure I keep track of my numbers. And we only ionize the AQ ones. Like this. And as before, you'll see that you've got chlorine on one side, 2 chlorines on one side, and 2 chlorines on the other side. We're going to cancel them because they're not involved in the oxidation or reduction. How do I know that? What's the charge on this chlorine? -1. Right there. It says chlorine -1. Ignore the fact that there's 2 of them. It's just chlorine is -1. Same on this side. So chlorine's charge, its oxidation number, did not change. So it's not involved in the oxidation reduction, which meaning its number didn't go up or go down. The other ones, I'll just rewrite it down here, you'll see have. So let's just write up our net right now. Oops, we don't have any chlorine. There we go. So it's just like this. Okay, and there is our net ionic equation. So what we'll do is, I'm just going to rewrite this on the next page here for me, is we can stick on our oxidation numbers. So why don't you go ahead and do that? I've already done them above, but let's put on our oxidation numbers on this reaction. And then identify where the oxidation and reduction is occurring. So let's just take, well, let's start at zinc here, I suppose. Zinc has gone from 0 to +2. So zinc has undergone an oxidation. Its number has increased from 0 to +2. So it has lost 2 electrons. Hydrogen, on the other hand, has gone from +1 to 0. So that is a reduction. And 2 electrons were gained, and that is for both hydrogens. Each hydrogen got 1. And that's basically it. So in class, what we'll do is, now what you should be doing is taking a look at the worksheet, and we'll just discuss some other things in class. Okay, so this unit is oxidation reduction, quite a bit different from the equilibrium stuff we've been doing the last little while. So first thing, we got to go back to some grade 10 material you may remember, and that is we have got on here. We shall stop the recording now, if I remember how.